Hello, my name is Guilherme. I'm a master's student at UFMG, Brazil. And today I'll be presenting the work that I did in collaboration with Professor Fernando, also from UFMG. The title of our work is Semiring Optimization, Dynamic Elision of Expressions with Identity and Absorbing Elements. So the whole goal of our work is to find and optimize statements like this. C equals C plus A times B. If we know that A or B is 0, in the end, what we're doing is C equals C plus 0. So you're not changing the value of C. This elision of expression, it depends not only on the form of the statement, but also on the inputs. And identity and absorbing elements, the first operation must admit an identity. And the identity is an element that when combined with others has no effect. So for instance, the identity of the addition is 0. If you add anything with 0, you get the other element. And the second operation must admit an absorbing element. The absorbing element is an element that when combined with others, you get the absorbing element back. So for instance, if you multiply anything by 0, you get 0 back. So to summarize, the goal of our work is to transform the code on the left into the code on the right, where if we multiply A and B, and if this multiplication is different than 0, sorry, if this multiplication is equals to 0, we don't need to compute the final expression. So is this optimization profitable? Well, if we represent this kind of expression in a tree address code format, we have two loads for A and B, one multiplication, another load for C, one addition, and a store. When we add the conditional, we are adding two instructions, a comparison and a jump. And if the jump is successful, we are avoiding three instructions. But if we know that A, for instance, is 0, then we can avoid 5 instructions. The load from B, one multiplication, the load from C, one addition, and the final store. So this optimization is profitable when the right-hand side is 0. But if it is not, then we are adding an overhead to the original source code. So this optimization is said to be speculative, like it depends on the inputs to be profitable. Finding the optimization opportunity in a small expression, in a small mathematical expression, is easy, but in longer expressions might be tricky. And we want to place the conditional as early as possible to avoid as many instructions to be executed. So how do we find the insertion point for any given expression? First, we build the AST for using the expression below. We build the AST. We get the first node, the root node, which is an addition. We get the identity of this addition, which is 0. And we propagate this information to the child on the right. We mark this node as red, and it means that this node is an insertion point. We get the absorbing element of this node. If this node has an absorbing element and the absorbing element is equals to the identity, we propagate to the child. So the absorbing element of a multiplication is 0, and 0 is equal to the identity of the parent node. So we propagate, we mark those nodes as red. The node on the left do not have an absorbing element, and the node on the right has. Like the node on the right is a binary end, and the absorbing element of a binary end is 0. We call the propagate function for the child node. If the node is a leaf, we marked it as red. And here's the final AST. So any node marked as right can be an insertion point. So now we'll talk about the solutions that we're proposing in this work. There are many ways to solve this problem, and we will propose 4 different solutions to implement this speculative optimization. Notice that this is a class compiler optimization. In the end, what we're doing is add an if condition to an arithmetic expression. And our final goal is to implement this optimization in a performance safe way. And by performance safe way, I mean, we don't want to add overhead in scenarios that this optimization is not profitable. So I will use the classic matrix multiplication algorithm to explain our proposed solutions. So here we have a semiring pattern. The first optimization that we proposed is called silent store elimination. And what it does, it only checks for a silent store. So here we compute A times B, and we check if the A times B is different than 0. If it is equals to 0, it means that what we're doing is adding 0 here. And if it is different than 0, this T0 will be something different. The second one is elision of absorbing element. In elision of absorbing elements, we use the notion, the algorithm that we explained before for finding insertion points to place the conditionals. In this proposed optimization, we want to place the conditional as early as possible. So in this case here, if A is 0, we will not load B. We're not going to do the multiplication, the addition, and the store. If A is different than 0, then we do the multiplication and the load of B. But if this if B is 0, then we will not do this part here. So elision of absorbing elements works and gives good results in the right scenarios. But this is still a speculative optimization. And in this case, adding a conditional to the source code will hinder the branch predictor and will prevent vectorization from happening. So these two branches here will prevent the compiler to apply vectorization. So what if we add profiling information to the program so that the program can decide at runtime if it will execute the code with branches or the original code? So now we'll talk a little bit about the profiling techniques that we propose. The first one is Intra-Loop Profile. In this optimization, we add a counter in the inner loop of the matrix multiplication algorithm. So we will add a switch and a default target that computes the original matrix multiplication algorithm. We add a counter called silent that checks how many times this T will be 0. We limit the number of executions for this default target. And if the silent divided by this number of iteration is greater than a threshold, we will execute after this number of iteration, this optimize branch, which contains if conditionals. Otherwise, if this silent threshold is smaller than the threshold, you just execute the original source code. Adding the switch here with those cases will still prevent the compiler from applying vectorization. So in this next proposed solution, which is called Pre-Loop Profile or PLP, we hoist the profiler to outside of the outermost loop. So the whole idea is we have a sampling function, sort of sampling function. And if the sampling function says that most of the times we have zeros on the inputs, we will execute the optimized version of the loops. Otherwise, we execute the original one. And this threshold that we put here, 0.5, was chosen arbitrarily. It can be any number. So how do we generate a sampling function automatically? And the answer is program slicing. Program slicing is the computation of the set of program statements that contributes to compute a point of interest in the program. So for instance, the first thing, like consider the original matrix multiplication algorithm, and we want to profile this point here, this value A of I times n plus k. We clone this loop to a function, which I'm calling sampling. So I'm marking here the nodes that are required the variables that are required to compute this statement here. We slice the program. We'll change the loop ranges. We add profile information. We limit the number of executions of this function. And we connect this function with move PLP. So now we'll talk a little bit about the evaluation that we're doing this work. So our hardware consists of an Intel Core i7 running at 3.4 gigahertz. We're using LLVM 6.0.1. Our benchmarks consist of the entire LLVM test suite. Our competitor, our baseline is Clang-03, and each experiment was executed 5 times. The first question that we want to answer is, do we find this ring pattern in LLVM, inside the LLVM test suite? So the answer is yes. This pattern happens in 126 programs, and the entire LLVM test suite is consisted of more than 250 programs. So 123 do not have the Semiring pattern. One program, like we're omitting some values, one program contains more than 140 Semiring patterns, and another one contains more than 400 Semiring patterns. We can see in this histogram that most of the programs out of this 126 contains 1 or 2 Semiring patterns. We will also report the data in the next experiment. We report the data only for 35 benchmarks, which are the ones that contains the Semiring pattern and runs for more than 1 second. So the Speedup. When we apply our optimization, like the 4 proposed solutions in those 35 programs, we have the following. VersaBench, like this BMM benchmark from VersaBench, the Speedup that we got on PLP, on the pre-loop profiling, which is the fastest solution that we're proposing, the fastest and safest in terms of performance, it got a Speedup of almost 3 times than compared to LLVM-03. We also have Koleski, LU, and LU decomposition that got Speedups close to 2 and greater than 1.5. We got some slowdowns as well. We have this global data flow FLT from TSVC. But you can notice that most of the programs, like in the PLP, they are a little bit, they are close to the baseline, which is LLVM-03. And this means that in programs that will not benefit from our optimization, the overhead that we add is close to 0. So you can see here that we have an X close to the 1 line here. We also compare our work with TACO, a specialized tensor algebra compiler. We are using the matrix multiplication algorithm to do this comparison with TACO. So we have this graph on the left, where the y-axis means the runtime in seconds, and the x-axis is the probability that the input matrix contains a 0. So for instance, a probability of 0.4 means that 40% of the input matrix is filled with zeros. Those 4 points here, DD, SS, DS, and SD, those are from TACO. And D stands for dense, and S stands for sparse. DS means that the first dimension is dense, and the second dimension is sparse. We can notice here that DS and SS, they decrease in runtime as the probability of zeros increases. We also have ORG, which stands for original, and PLP for pre-loop profiling, and those are from our solution. The original, it's the original matrix multiplication, and PLP is the pre-loop profiling. And we can see that the original stays pretty much the same as the probability increases, And our solution follows the original and switches to follow TACO when the probability changes from 0.5 to 0.55. For the conclusion and final notes, this work introduced the notion of semi-ring optimization. We showed how to implement this optimization in a performance-safe way. We have an average speedup of 1.06 in those 35 programs from the LLVM test suite. And when combined with semi-ring optimization, LLVM can generate code which can achieve speedups close to TACO, which is a specialized tensor algebra compiler. Today, our work is available at this location, and we welcome interest developers in research to write to us with questions, comments, and suggestions. Thank you very much for your attention.